Alright, now we're going to learn about factoring quadratic equations. So if you want to go from standard form into factored form, how do you do it? First, let's remember what is factored form. So factored form is the equation for a parabola that looks like y equals a times x minus r1 times x minus r2. And remember, r1 and r2 are the roots. And remember, root means x-intercept. Okay. So the idea is we're going to take an equation that's in standard form and convert it into this kind of factored form. The way to do that is to think about how we went from factored form into standard form. So if a is equal to 1, it helps us out a lot, because then we have, in standard form, y equals, instead of a, you just have x squared plus bx plus c. Okay, and what we had when we wanted it in factored form was y equals x minus r1 and x minus r2. Okay. So if we look at how to get between these two forms, we already know how to get from this form to this form. We FOIL it out. If we were to FOIL this out, we would get x squared minus r1x minus r2x plus r1 times r2. Okay, so we can see by comparing this expression to this expression that the c value has to be r1 times r2, and the b value has to be basically the opposite of r1 plus r2. And so, because when we do the factoring, instead of thinking of the roots with a minus sign, we first just try to figure out, okay, what number goes here, what number goes here, and then we know the root is the opposite of that. So it turns out this minus sign in the front, that's just telling us the roots are going to be opposite of whatever we get, so we can kind of ignore that when factoring, and then remember it when writing down what the answer is. So the b value is going to be the sum of two numbers, and the c value is going to be the product of two numbers. So we're looking for two numbers that multiply together and give us this c value, and add together to give us this b value, and then we can put them into this expression. Except in this case it's going to be x plus, say, number 1 and x plus number 2, because we've ignored that minus sign right there. I hope this makes sense. As soon as I do a couple examples, I think it will. So that's how we do it. I'm not going to do an example here, but when we get to class we'll do a bunch, or maybe at the end of this video. Okay, if you're coming from standard form, but the leading coefficient a is not equal to 1, things get a lot trickier. So if you have y equals ax squared plus bx plus c, you want it to be into factored form. Option 1 is to try to factor out this a value, and then if you factor out a, you're left with x squared plus b over ax plus c over a. Now this is a little bit of something new. We've learned factoring, but if you take the a out, if you distribute it back in, think about what you have ax squared. If you distribute it back in here, the a divided by a cancels, and you're left with just bx. And if you distribute it back in here, the a and the a cancel, and you're left with just c. So I hope this seems reasonable that you could factor it out. It makes more sense with numbers. So say we have y equals 2x squared plus 6x plus 4. You see they all have a 2 in common. So you factor out the 2, and you're left with x squared plus 3x plus 2. So this is just a way to write it with the variables. But what we really mean is factor out what they have in common, and then you can factor this part normally. Right? So because now that you've factored out the stretch factor, the part that's left over would just have a leading coefficient of a 1, and so you can factor this normally, and so your final answer would be like 2 times, let's just finish this example. You need two things that multiply to 2 and add to 3. So that's going to be a 2 and a 1. So x plus 2, x plus 1. So your roots are negative 2 comma 0. Remember, because it's the opposite sign here. And negative 1 comma 0. So those would be your roots. But the idea is, if you have a leading coefficient, try to factor it out, and then see what you have left, and then you can factor that the other way. The alternate option is to do this what I call smart guess and check. So if you have something like y equals 2x squared plus, let me think of an example real quick, 5x plus 2. Okay, you can know, now you would think first, let me try to factor out a 2, but 2 doesn't go evenly into all of these numbers. Okay, so you know that you're eventually going to get a set of parentheses like this. And you know that the last two numbers have to multiply to give me a 2. So the only really option I have is a 2 and a 1. And now instead of having just an x squared here, so we would normally put an x here and an x here, but because I have a 2x squared, I'm going to need to put 2x times x. So then the question is, do I put the 2x here and the x here, or vice versa? So to do smart guess and check, you have to be kind of thinking about what two things multiply to this that go in the front and the front, what two things multiply to this that go in the back and the back, and then I have to put them all together in the right order so that my middle term comes out to be what I want it to be. So I could try putting a 2x here and an x here. If I do my outers, I get 2x times 1, and if I do my inners, I get 2 times x, which is 2x and 2x. But 2x and 2x, outers and inners, they don't combine to give me 5x, so that's no good. What if instead I have my 2 and my 1, I put my x here and I put my 2x here. Now my inners is a 4x and my outers is a 1x, and those combine to give me the 5x that I want. So when I say guess and check, I mean you're doing guess and check, but you're thinking about what you want and being clever about what choices you make. And it's not super easy. I mean, it takes a lot of practice and it takes a lot of time to see what you want to use. If you have a number that's a 2 or a 3, it helps a lot because the only way you can multiply to a 2 is 2 times 1, or the only way you multiply to a 3 is a 3 times 1. But if you have a 6 or an 8, or even a 4, you could have like 3 times 2 or 6 times 1 for a 6. For an 8, you could have 4 times 2 or 8 times 1. So the more factors a number has, the more tricky it becomes. The last thing I want to say about this one here is this is your answer for factoring it, but you have to be extra careful when you're looking at your roots. So let's see what the roots are. Here we had x plus 2, so the root is negative 2 comma 0. This one we have 2x plus 1. Now normally, factored form says that you need to put this in x minus r1, which is what we have for the first term, so y equals, and x minus r2 for the second one. But you notice that this is a 2x plus 1, not just an x plus 1. So because it's not in this factored form, the root for the second one is actually not equal to negative 1. Because of this 2x right here, the root is actually going to be negative 1/2 comma 0, and I'm going to show you why in about a slide or two, why that is. So we'll talk about how to get the roots out of factored form if it's in this kind of modified version where instead of just having x plus r1 or x minus r1, you have a 2x or a 3x or anything else like that. I promise I will tell you very soon. But one slide before that. So the previous two slides were how to get the factored form out of standard form. So you do that by factoring. Okay, there's a completely different way to do it if you start in vertex form. If you start your equation in vertex form, you've got y minus k equals a x minus h squared. So if you want to get the equation in factored form, this requires getting the roots. Okay, so if you can get the two roots, which is the x-intercepts, then you can just write down the answer in factored form. So the task here is instead of trying to factor it, we're going to try to solve it to get the two roots and then write the answer in factored form. So we're going to solve this guy, and the way that you solve it is just like back in section 9.1, solve for x. So move everything away, take the square root of both sides, branch, and you're going to get two answers. Those two answers that you get are your roots, and once you have your roots, you can write the answer in factored form. So you have to set y equal to 0, otherwise you have another variable in here. It's okay to set y equal to 0. In fact, it's important to set y equal to 0 because you're finding the x-intercepts, and the way that you find an x-intercept is by setting y equal to 0. So let's give an example. Y minus 3 equals, let's say 1 x plus 4 squared. So let's solve this. First we set y equal to 0. So we have, oh, I can't do that. Sorry. If I set y equal to 0, this will be negative 3. And when I take the square root, it won't work. So let me go plus. Okay, so say that's our starting off problem. Now we're going to set y equal to 0. So now we just have 3 equals x plus 4 squared. Solve for x. Take the square root of both sides. So we have x plus 4 equals plus or minus the square root of 3. Then we subtract 4 from both sides. Then we have x equals negative 4 plus or minus the square root of 3. Okay, so we can get answers for these two. And we get roughly, square root of 3 is about 1.7. So negative 4 minus 1.7 is negative 5.7. And negative 4 plus 1.7 is negative 2.3. So those would be my two x-intercepts. And so to write the equation in factored form, I just write y equals x plus 5.7 times x minus, x plus, sorry, I'm making a mistake. I apologize. These are my two roots. So I get y equals x plus 5.7 for my first one, because if I plug in negative 5.7 into factored form, I change the sign and I get that. The other one is negative 2.3. So when I plug x minus a negative 2.3, it becomes x plus 2.3. Okay, so that would be my equation. Now, of course, these are rounded values because I had a square root of 3, which is an irrational number, so it was an infinite decimal. But if I round it, I get these two values, and I would get this as my answer. And if you look at the graph of this thing, this original equation has been moved left 4 and down 3. So I go left 4 and down 3. I put my vertex. And then I draw on my parabola. It's going to look something like this. 4, 5, 6. So you can see this root here is at negative 2.3, something like that. And this root here is at negative 5.7. And if you go even back one step farther, it matches up what you think, because you have negative 4 plus or minus the square root of 3. The negative 4 is right here, which is the center of it, and then the plus or minus is to the left or to the right to get these two vertices. And the reason it's a square root of 3 is because the vertex was down 3. So we went over square root of 3. Square root of 3 squared is up 3. If that doesn't make sense, don't worry about it, but if it does make sense, it's a cool connection that you can make in terms of the way that you graph it, the way that you have it in one form, and the way that you have it in another form. They're all super interrelated. Okay. The last thing here is what's called the zero product property, which is what I promised I would talk about a couple slides ago. So if you have an equation like the one we had, y equals, say, x plus 2 times 2x plus 1. Okay. In order to find the roots, you know that the y value has to be 0. So the roots, y equals 0. So if you plug this in, what that means is when we multiply x plus 1 times 2x plus 1, x plus 2. Let me fix that. X plus 2. When we multiply these two things together, they have to equal 0. The only way that you can multiply two numbers together and get 0 is if one of those two numbers starts off as 0. So they have two options. This whole thing equals 0, so maybe x plus 2 equals 0, or maybe this thing equals 0. But at least one of these two things has to be 0, otherwise there's no way that the product of the two would be 0. So if you solve this equation that you get here, you subtract 2 from both sides, you subtract 2, you get x equals negative 2. So this is actually the reason why the root is the opposite sign of whatever number you have right here. It's because the value has to equal 0 overall. So we always asked, what number would you plug in to make it 0? So if you have x plus 2, the number you plug in to make it 0 is negative 2, because negative 2 plus 2 is 0, and you multiply by 0, you get 0. Over here, though, you can't be quite as hasty. You see this plus 1 right here, and you might think, oh, if I plug in negative 1, it will be 0. But that's because it used to be just x plus r, or x minus r, but now we have a 2x, so when you subtract 1 from both, subtract 1, cancel, 2x equals negative 1, then you have to divide by 2, and you get x equals negative 1/2. So the actual root is not the full value that you see right here. So the zero product property says that if you have 0 equals a times b times c times ... any product of terms, you have to have a equals 0, or b equals 0, or c equals 0, etc. So in order for things to multiply up to get 0, you have to have at least one of them equal to 0. And so you have in factored form, you have a product of terms, namely this factor times this factor, equaling 0 to find the roots. You put in y is 0. And the only way that can happen is if these guys are 0 independently. So you can take the piece that's in factored form, set it equal to 0, and then solve. So try to write a sentence in your own words right now in your notes that summarizes that. So in factored form, each term or each piece that you have, whatever you want to call it, can be set equal to 0 and then solved for x, and that's the value of your root. So it is the opposite sign of what you see in the simplest case, but it can also be a little more tricky if you have a 2x or a 3x or a 4x or something right here. One more thing I'll say, just to cap it off. Ultimately, you could factor a 2 out of this expression. So if you factor this out, you'd have a 2. What you'd have left behind is an x plus 1/2, if that makes sense. So the 2 can be written in the front as a stretch factor, and then the other root, you see x plus 1/2, so you know that the answer is negative 1/2, which is what we ended up getting down here. So again, there's lots of ways to interconnect all the stuff that we're learning, and it's kind of up to you to form your own ideas and mental structure on how the pieces fit together and how it makes sense to you. So come in with any questions that you have, and I'm happy to discuss this further in class.